Electronic waste, challenges, resource recovery, and emerging sustainable technologies. Electronic waste, e-waste, has emerged as one of the fastest growing and most complex waste streams of the modern technological era. Driven by rapid innovation, shortened product life cycles, and increasing global consumption of electronic devices, the accumulation of discarded electronics presents both a severe environmental burden and a significant opportunity for resource recovery. According to the United Nations Institute for Training and Research Global E-Waste Monitor 2024, approximately 62 million metric tons of e-waste were generated worldwide in 2022. This volume reflects not only the scale of technological reliance but also systemic inefficiencies in material recovery and waste management. Economic and environmental implications of e-waste. A striking feature of e-waste is its intrinsic value. The discarded electronics generated in 2022 contained an estimated $91 billion worth of recoverable metals, including copper, iron, gold, aluminum, platinum, and rare earth elements such as neodymium. These materials are essential for advanced technologies, particularly in renewable energy systems, electric vehicles, and electronic infrastructure. Despite their importance, nearly 40% of these metals were not recovered and instead were landfilled, incinerated, or handled through informal and uncontrolled processes. Only a small fraction, approximately 4% of certain critical metals, was successfully recycled, underscoring a major inefficiency in global resource utilization. From a societal perspective, e-waste generation is closely linked to consumer behavior and economic development. In 2022, the average individual in the United States discarded approximately 21 kilograms of electronic devices, while in Norway, the highest per capita producer, the figure reached 27 kilograms. These statistics illustrate the rapid turnover of electronic products, often driven by technological obsolescence, limited repairability, and consumer preference for newer models. Devices such as smartphones, laptops, and gaming consoles frequently accumulate in households before eventually entering the waste stream, contributing to the growing volume of e-waste. The environmental implications of this trend are profound. Mining virgin metals to meet global demand is associated with habitat destruction, soil and water contamination, high energy consumption, and greenhouse gas emissions. Furthermore, mining operations are often linked to geopolitical tensions and ethical concerns, including labor exploitation. Recovering metals from e-waste, commonly referred to as urban mining, offers a compelling alternative. It has the potential to reduce dependence on primary extraction, lower environmental impacts, and contribute to a circular materials economy. Estimates suggest that efficient recycling of e-waste metals could prevent tens of millions of metric tons of mining-related greenhouse gas emissions annually. E-waste management. Despite these advantages, global recycling rates remain low, with less than a quarter of e-waste being formally collected and processed. A substantial portion is handled by informal recycling sectors, particularly in developing regions, where crude techniques such as open burning and acid leaching are employed. These practices release hazardous substances, including mercury, lead, and brominated flame retardants, posing serious risks to human health and the environment. Additionally, a significant share of e-waste is disposed of in landfills, where toxic components can leach into soil and groundwater. Several factors contribute to the inefficiency of current e-waste management systems. Inadequate regulatory frameworks, insufficient infrastructure, and lack of consumer awareness play central roles. Moreover, the design of electronic devices themselves presents a major challenge. Modern electronics are highly complex, often containing dozens of elements in small quantities and intricate configurations. For example, a single smartphone may contain over 40 different metals, many of which are present in trace amounts. This complexity makes separation and recovery technically challenging and economically unattractive using conventional methods. Traditional recycling processes rely heavily on pyrometallurgical and hydrometallurgical techniques. Smelting, a widely used method, involves high-temperature treatment of shredded e-waste to extract metals. While effective, this approach is energy-intensive, generates significant carbon emissions, and produces toxic byproducts that require extensive treatment. Hydrometallurgical processes, which use strong acids or bases to leach metals, also pose environmental and safety concerns due to the use of hazardous chemicals and the generation of secondary waste streams. Innovations in e-waste management. In response to these limitations, researchers and industry stakeholders are developing innovative approaches to improve the efficiency, sustainability, and economic viability of e-waste recycling. Among the most promising strategies are biologically mediated processes, advanced chemical extraction techniques, and electrically driven recovery methods. Biotechnological approaches, often referred to as bioleaching or biorecovery, utilize microorganisms or biomolecules to selectively extract metals from complex waste matrices. Certain bacteria have the ability to accumulate metals such as gold and rare earth elements from solution. For instance, species like Vibrio natrigans and Shewanella onidensis have demonstrated the capacity to adsorb rare earth elements, offering a potential pathway for recovering these critical materials. Advances in genetic engineering have further enhanced the efficiency of these organisms, enabling higher uptake and selectivity. Beyond whole cell systems, researchers are exploring the use of metal-binding proteins. A notable example is lanmodulin, a protein with a strong affinity for lanthanides. By immobilizing such proteins on solid supports, it becomes possible to selectively capture and separate rare earth elements from mixed metal solutions. This approach offers advantages in terms of specificity, lower chemical usage, and reduced environmental impact compared to conventional separation methods. Chemical innovation also plays a critical role in advancing e-waste recycling. Novel solvent systems and selective leaching agents are being developed to extract metals under mild conditions. For example, proprietary solutions capable of dissolving gold at room temperature within minutes have been demonstrated at pilot and industrial scales. These processes significantly reduce energy consumption and eliminate the need for high-temperature operations, thereby lowering both environmental footprint and operational costs. Another emerging technology is flash joule heating, an electrically driven method that rapidly heats e-waste to extremely high temperatures using short pulses of electric current. This process vaporizes metals, which can then be condensed or dissolved for subsequent separation. Compared to traditional smelting, flash heating is more energy efficient because it directly targets the material rather than heating an entire furnace. Additionally, it reduces the number of processing steps and minimizes the generation of secondary waste streams. Complementing these approaches are innovative hydrometallurgical processes that leverage fundamental chemical principles such as redox reactions and ion exchange. For instance, copper-based solutions can selectively dissolve rare earth elements from shredded electronic components, enabling their recovery without extensive pre-treatment. Such methods highlight the potential of simple, scalable chemistries to address complex recycling challenges. Limitations and future perspective. Despite these technological advances, the successful implementation of sustainable e-waste recycling systems depends on economic viability and scalability. Recycling operations typically operate on narrow profit margins, and the recovery of metals present in low concentrations may not be financially attractive. Therefore, improving process efficiency, reducing costs, and increasing recovery yields are essential for widespread adoption. Integration of recycling facilities into urban environments, where e-waste is predominantly generated, can further enhance efficiency by reducing transportation costs and enabling localized processing. Policy and regulatory frameworks are equally critical in driving progress. Current regulations often emphasize overall recycling rates by mass, which can inadvertently prioritize the recovery of bulk materials such as plastics over valuable but low-concentration metals. To address this imbalance, targeted policies that incentivize the recovery of critical elements are needed. Extended producer responsibility (EPR) schemes, eco-design requirements, and stricter collection targets can encourage manufacturers to design products that are more durable, repairable, and recyclable. Equally important is the recognition that recycling should not be the primary solution to the e-waste problem. Strategies such as product reuse, refurbishment, and repair offer greater environmental benefits by extending the lifespan of electronic devices and delaying their entry into the waste stream. Designing electronics for modularity and ease of disassembly can facilitate these practices, reducing the need for resource-intensive recycling processes. Consumer awareness and participation also play a vital role. Proper disposal and recycling of electronic devices require accessible collection systems and public education initiatives. Without active engagement from consumers, even the most advanced recycling technologies will struggle to achieve meaningful impact. In conclusion, electronic waste represents both a critical environmental challenge and a valuable resource reservoir. While current recycling rates are insufficient to capture the full economic and environmental benefits of e-waste recovery, emerging technologies in biotechnology, chemistry, and materials processing offer promising pathways toward more sustainable solutions. Achieving a circular economy for electronic materials will require coordinated efforts across technological innovation, policy development, industrial practice, and consumer behavior. As global demand for critical metals continues to rise, the efficient recovery of these materials from e-waste will be essential for ensuring resource security, environmental sustainability, and the transition to a low-carbon future.